no, I didn't. Okay, so last time we ended with, we had just barely done the decarboxylation. You oxidize isocitrate to oxalosuccinate, oxidize the secondary alcohol to a ketone. Then you have a beta keto acid. Yep. You can't see. I'm pointing at stuff. Why aren't you seeing it? If you close your eyes, can you see it? Still can't see it. Okay, thank you. That is, forgetting to unblank the projector is another extra credit point for everybody that's here. So. I did start the recording now. Yeah. Too bad. Okay, sorry. We'll just back up there. We talked about formation of isocitrate. We talked about oxidation of the secondary alcohol to form a ketone. That there you have now a beta keto acid, and those can undergo spontaneous decarboxylation because the leaving group is a resonance stabilized enolate. And we got to this point of alpha ketoglutarate, which we noticed is an alpha keto acid. And where I left you was to have you go back through learning from what you saw in the pyruvate dehydrogenase complex, and then have you go through the decarboxylation of alpha ketoglutarate, which is just like pyruvate, only it has an R group instead of a methyl group there. Okay, so that's where he ended up. I know you're preparing for exams, so I'm not going to ask you if you did it or not. We're not going to show hands. But it may be worth looking at this, which I think is a part of the problem set for key. So to alter what I've drawn here for the pyruvate dehydrogenase complex for alpha ketoglutarate, we would simply need to add an R group there. I'm not going to do that. I'll just have you imagine that. Remember that in this process, TPP acts like, and TPP that's thiamine vitamin B1, acts as a nucleophile to attack the ketone, break the pi bond, and protonate. You get this intermediate, and now the carboxylate can act, the negatively charged oxygen can act as a kicker offer, because the electrons in the bond between the carboxylic acid carbon and the alpha carbon can go on to the alpha carbon where they're stabilized by resonance with the pi bond from the TPP group. And that's shown here. Ooh, that's kind of ugly. I got to redraw that because I drew it. There we go. Okay, that's better. The lone pair electrons on the carbon that came from this bond are now adjacent to a pi bond where they're stabilized by resonance. Okay, so you get that intermediate. You then form, using the negative charge on this carbon, you form a new carbon-sulfur bond with the lipoamide disulfide. This is a direct substitution reaction. Lone pair electrons attack this sulfur, attack the sigma star associated with that bond. You break the bond and protonate this group as it leaves. Then lastly, the enzyme removes a proton from the oxygen, which then kicks down and kicks off TPP as a leaving group. And now you've converted your what used to be alpha keto acid into a thioester, and you've lost a molecule of CO2. At that point, getting acetyl-CoA is a simple thioester exchange reaction. Coenzyme A attacks the first thioester. You get a tetrahedral intermediate, which kicks down and kicks off the other thiolate as a leaving group. And then you get acetyl-CoA, or in our case, succinyl-CoA, because this would be an R group. And then you get this dithiol, which later on gets oxidized through a mechanism we didn't talk about and aren't going to talk about. to get you back the disulfide. So that's probably the most complicated mechanism that you've seen so far this semester. I don't know that it ever gets worse than that. So if you're working your way through that and feeling good about it, that's good. Any more questions about this process, how it happens? Okay, well, let's move on from there. Just to remind you where we're going, having made succinyl-CoA, we're now down to 4 carbons. So our task from this point on is to get to oxaloacetate so we can start the cycle again. So there are, let's see, 1, 2, 3, 4 steps. The first one is maybe the most complicated, and then the steps after that are relatively simple. But this is where we're going to recover the bulk of our energy-rich molecules, GTP, FADH2, and NADH. All right. So the mechanism starting with succinyl-CoA and ending with succinate, notice that looks like a simple thioester hydrolysis. But it turns out along the way, because going from thioester to carboxylate is so downhill in energy, we're going to use that energy downhill to create another high energy molecule, GTP. In other words, we're going to pay for making a phosphoanhydride in GTP by hydrolyzing a phosphoester in succinyl-CoA. So the intermediates are all shown here, and this uses an unusual mechanism that we haven't seen before, but it's straightforward enough to understand. Compare succinyl-CoA with this intermediate, understanding that this is the carbonyl carbon, this is the carbonyl oxygen, and phosphate dianion is acting as your nucleophile. That means the thioester is your electrophile. If it's the electrophile, we care about the LUMO. What is the LUMO of the thioester? Carbon, oxygen, pi star. Good. Notice that we're ignoring the carboxylate. Why? Because that's level 4 and thioester is level 1. So tell me what arrows I should do. Where should they start? Where should they end? Lone pair on phosphate oxygen. Good. Then what? To the carbonyl carbon and break the pi bond, always. Good. So that gets us to this tetrahedral intermediate. The coenzyme A thiol group is going to be the leaving group. This was our nucleophile in the previous step. This used to be our carbonyl carbon. This is going to be the oxygen kicker offer. So how do I show that happening? Where does my arrow start? Okay, lone pairs on the oxygen, doing what? Kick down, and who do I kick off? Yeah, this one, but how can I tell? Because it's gone in the product, right? So that's how you can tell when a leaving group leaves. Look at the product and see if it's still there. Good. All right, so coenzyme A thiolate leaves. We now have converted our thioester to an acyl phosphate. This is the acyl phosphate group. And remember that acyl phosphates, like thioesters, are also level 1. So no big change in energy at this point. Now, the interesting thing about acyl phosphates is that they are electrophilic at 2 different positions. So they are electrophilic at the carbonyl carbon. So you could look at an acyl phosphate and say, oh look, carbonyl carbon, carbonyl oxygen, leaving group. And that's one perspective that's valid. Another perspective that's equally valid is to say, hey look, electrophilic phosphorus, phosphoryl oxygen, leaving group here. And this leaving group would be a carboxylate, which is also the conjugate acid, the conjugate base of a strong acid. So acyl phosphates are tricky because they have dual character. And you don't really know, depending on the reaction, whether your nucleophile should attack the carbonyl carbon or the phosphoryl oxygen. That's why you have to pay attention to what's going on in the reaction. So if I look at the next reaction, I start with my acyl phosphate and I end up with an intermediate where some enzyme side chain is now bonded to the phosphorus. That's a clue that my mechanism should involve attack on the phosphoryl group and breaking of the phosphorus oxygen pi bond. So just by comparing starting materials to products here, I can tell we better attack the phosphorus oxygen pi star and break the phosphorus oxygen bond. Now, you might ask the question, why can't GDP be the nucleophile and just directly attack this phosphorus? That's certainly what happens in glycolysis with the 1,3-bisphosphoglycerate step. ADP attacks the phosphorus directly. I don't know why the enzyme evolved to do what I'm going to show you, but this is what the data suggest. The enzyme is going to deprotonate this side chain group. This side chain is called histidine. And base will remove the proton from histidine. Electrons will shift over like this, and then the nitrogen will attack the phosphorus, and you break the phosphorus oxygen bond. And that leads to this intermediate. Again, in that intermediate, the phosphorus is there, the phosphoryl oxygen is there. Our leaving group is this carboxylate. So and of course the enzyme side chain was the nucleophile. Electrons here on the negatively charged oxygen are going to kick down, restore the pi bond, and the leaving group leaves. And that generates our succinate as a leaving group. And now the phosphate group is attached to the enzyme here. This is weird. This is a functional group you haven't seen before, and we don't need to have a name to call it, other than we're going to say this is a leaving group. And it's in the enzyme active site. So now GDP can come into the enzyme active site. We're going to attack the phosphorus, as we've done before, get an intermediate in which 5 things are now bonded to what used to be the phosphoryl group. GDP was the nucleophile in purple. And the enzyme side chain is going to be the leaving group. And as with a lot of other leaving groups, an acid is going to help it leave. Electrons on the phosphoryl oxygen will kick down, and then the leaving group leaves. As it does, it's going to get protonated on the other nitrogen like this. And that gives you your GTP product, and then that restores the enzyme to the starting state. So overall, we converted a level 1 thioester to a level 1 phosphoanhydride. And so this reaction is not hugely downhill, pretty reasonable. And the gamma phosphoryl group that's now on GTP came from this phosphorus nucleophile. All right, kind of involved the players. This would be difficult to predict, but once you see what the intermediates are, can you see how it's just addition of a nucleophile to a reactive carbonyl group, tetrahedral intermediate, then kick off a leaving group, and then we do it again, and then again? Okay, that's the pattern you're looking for here. Questions about that? Yeah.
What causes that tissue after the GDP on the next one?
What causes what after the GTP?
Sorry, I just can't see very well. So we have the lone pair come down to form a double bond on the phosphate.
Yes.
And then
And
what causes, does it detach because one's a better leaving group versus the other as far as the
right, it's a good question is why don't we just from this point kick off GDP, and I suppose that can happen. I think the presence of this acidic group in the enzyme site, in the enzyme active site, helps make this a better leaving group as it's leaving. Protonated as it's leaving. Yeah. Okay, others? All right. Let's take a look at the next step. If you look, maybe I'll scroll up to our overview of the citric acid cycle. In the next step, we're going to start, I'm going to erase what I drew before. We're going to start with succinate, which is a 4-carbon diacid. And ultimately, we want a ketone on one of those carbons in the middle, so that can be oxaloacetate. So that's going to require some oxidation. And this happens in 2 different oxidation steps and an addition step. The first is the oxidation step. You can tell it's an oxidation step because the enzyme is named succinate dehydrogenase. Remember, enzymes are named according to substrate, which is succinate, and then what they do, which in this case is oxidation, and dehydrogenase describes an oxidation/reduction reaction. In this case, we're using a different recipient of an oxidizing agent, and that's called FAD. This is like NAD+, but it's neutral. And you can think of FAD as a hydride acceptor, and at the same time, it's also a proton acceptor. A hydride is a hydrogen with 2 electrons, H-. A proton is just a hydrogen with no electrons, H+. FAD receives both of them, and that's why when it's in its reduced form, it's called FADH2. And we'll talk about the structure. You can tell that this is an oxidation reaction because before the reaction, the molecule had 4 CH bonds, and after the reaction, the molecule only has 2 CH bonds. Where did the electrons from this pi bond come from? Where did they come from? They came from one of the CH bonds. So from the perspective of FAD receiving stuff, this is the proton it receives, and then this is the hydride that it receives. So the molecule is going to remove, the reaction will remove a proton from this carbon, electrons will kick down, and H- will leave, being received by FAD to give FADH2. So if you go to your quiz, I've drawn you the structure of FAD, only the part that matters. This part is called flavin, and it's part of riboflavin, which is vitamin B2. And it doesn't look quite like NAD+, because it doesn't have the positive charge, and it's a little bit more difficult to determine where the electrophilic atoms are. So I'm going to attempt to show you this by showing you a resonance structure that tells you which atoms are electron rich versus electron poor in this molecule. So if I take these pi electrons between this nitrogen and this carbon, and I move them over to form a pi bond here, then I would also need to move the electrons from this pi bond over onto this far nitrogen. If I did that, I could draw a resonance structure of FAD that would look like this. This nitrogen, which I just took electrons away from, would have a positive formal charge. There would be a pi bond here, and then this nitrogen I just gave electrons to it would have a negative formal charge. And of course, that negative formal charge could be stabilized by resonance with this adjacent carbonyl group. And then I'm missing another nitrogen, aren't I, right there? And then an R group. So when you look at FAD, this is the nitrogen that's electron poor, and this is the nitrogen that's electron rich. This nitrogen is going to be the hydride acceptor, and this nitrogen is going to be the proton acceptor. So we can show this happening here. Where do you think I should start my arrow, and where should it go? If you're stuck, remember that succinate has 4 CH bonds, whereas fumarate, the NIPA product, has only 2 CH bonds. So it makes sense that a proton has to be removed somewhere. And remember also what you've learned, which is that alpha protons are acidic. When you can't figure out what to do, remember the fact that alpha protons are somewhat acidic. So with that in mind, remove a proton. Electrons here kick down to form a pi bond. H with its electrons is going to be the leaving group. And it will leave but be directly handed off to this nitrogen. Electrons will kick down from that nitrogen to form a pi bond here, and then the resulting negatively charged nitrogen is going to pick up a proton from an enzyme side chain. So this oxidizes succinate to fumarate. Again, if I'm going to highlight, this is the proton that gets removed. I guess I'll color it orange. The proton that gets removed ultimately is picked up from the enzyme in this step. And then in green is the hydride that gets delivered to the molecule. So FAD has 2 additional hydrogens, and it removes 2 hydrogens from succinate, and that's why the reaction is called catalyzed by succinate dehydrogenase. That's a little bit more complicated than an NAD plus mediated oxidation. FADH2 is a little bit different than NADH. It has a different reduction potential. It intercepts the electron transport chain at a different spot, and therefore results in a slightly different proton gradient. We'll talk about the electron transport chain tomorrow. But each FADH2 is only worth 1.5 ATP instead of 2.5 for NADH. All right, questions about that oxidation step? If you look at it, it's a deprotonation and an elimination step. Yes?
Does for the FAD to fulfill this reaction, does it need both the hydride and proton?
Yes, for FAD.
You just take one at a time?
Yeah, actually, the chemistry of FAD is more complicated than NADH. There are some weird things known to happen with FAD, but in this case, no. In this type of reaction, you always transfer a hydride and a proton. So it's sort of, you guys learned early on in this class when we were talking about fats and oils about the hydrogenation reaction, hydrogenation of unsaturated oils, where you deliver H2 across a double bond using a palladium catalyst. This is how you get hydrogenated vegetable oil, or Crisco, which is a solid instead of a liquid. This is the backwards reaction of that. This is start with an alkane and then remove hydrogen to get an alkene. Okay, other questions? Okay, we're getting close. Next is a reaction that is very similar to something that you've seen before. So I'm going to have you try this one on your own. This is a hydration reaction, and it is very much like the reaction of a conatate to isocitrate. All right, a conatate to isocitrate. So take a minute and see if you can work your way through that one. Feel free to consult your notes from last time on isocitrate. I'll also give you a hint. Remember that carbons that are beta to carbonyl carbons are electrophilic. In this case, you don't need to worry about the fact that there are two different beta carbons in this molecule. The two carboxylates are identical. Just pick one and get started there. All right, see what you can do. Take a few minutes to do that. Stuck? Any questions? All right, well, anybody feeling brave? Promise not to tease or criticize. Go ahead. Yeah, thank you. Whoa.
Okay. Well, we have water that the base will take the proton off of, and then these electrons will attack that beta carbon. I think. That will break this pi bond, which will then deprotonate the acid, and then that will make the L malate.
Okay, good. One more arrow. I would just, I totally understand what you're doing. Take the electrons between the H and the A and move them onto the A.
Oh yeah.
Yep. Good. Excellent. Good. So that's the hydration reaction. Thank you. Well done. This reaction allows us to, are there any questions about that? Anything you want to talk about? One interesting feature is that you start with fumarate. Is this molecule chiral? That's a skill you haven't tested in a while. Probably better test that one before you get to the final. Is that molecule chiral? By which I mean, is it the same as its mirror image or different? It's the same, so the molecule is not chiral. How about the product? Is that chiral? How can you tell? You are right. How can you tell? Yeah, this carbon 3 is a stereocenter. You can tell the molecule has just this stereochemical configuration because they don't just call it malate, they call it L-malate. L and D, as I talked about, is an old-timey way of talking about chirality. We don't need to go into it in a lot of detail. We now use R and S. We could assign stereochemistry at that carbon. Go ahead and do it. See if you can do it on the fly. You haven't reviewed it. See if it's still up there in your head. Yep, I want the R versus S configuration of that stereocenter. No fair flipping a coin. Give you a hint, you should draw the proton that is implied but not shown. Okay, have you got a conclusion yet? Anybody? Raise your hand if you've got a conclusion. If you don't, that's okay. Let's still review it. A couple more seconds. All right, you got an answer? I'm going to make you vote and commit. So, and to avoid pressure, everybody close your eyes except you, where it won't matter if you close your eyes, you're still going to see it, right? Okay, everybody close your eyes. People that voted S? People that voted R? Okay. Good. Let's see what the right answer is. I don't actually know. I have to figure it out. This is group 1. This is group 2. This is group 3. Priority 3. And then hydrogen is 4. You can tell oxygen is 1 because it's heavier. These two are both carbons, but this one is bonded 3 times to oxygen. This one is bonded to carbons and hydrogens. Oxygen wins. So 1 to 2, 2 to 3, 3 back to 1, and it's counterclockwise with group number 4 is down away from us, so indeed it is S. Okay, good. If you got it wrong, don't worry, you had a 50-50 shot, but that may be worth correcting because I have to write a final and it's very easy to write RS questions, and I will probably take the easy way. Yes?
So is L always S?
Good question. Is L always S? within a class of closely related molecules, that usually follows, but it doesn't follow universally. L and D were assigned by analogy to other compounds. There was and I forget the whole story, but so I should just stop while I'm ahead. But anyway, there's no direct correlation with S and R. Okay, other questions? So now the last stage is oxidation of malate to oxaloacetate. We can look real briefly at the citric acid cycle, but actually we're not going to. You want to look in your notes, you can. Notice that malate is a secondary alcohol, and in oxaloacetate you want to oxidize it to, in oxaloacetate, that secondary alcohol is going to be a ketone. Now, you've seen, whoa, that's actually not the right thing, is it? There we go. You've seen a reaction that oxidizes malate, or that oxidizes a secondary alcohol to a ketone. First, tell me, if you didn't know the enzyme, what would you guess it is? Yeah, dehydrogenase, because you're starting with a secondary alcohol, malate, and you're going to a ketone. That's a redox reaction. That's an oxidation reaction. And probably if you had to name the substrate, you just call it L-malate dehydrogenase, and that would be pretty close. I'll tell you that the thing that receives the hydride is NAD+. You probably could have guessed it based on things that you've done before. So now with that in mind, and if you need to go in your notes and look up the structure of NAD+, that's fine. I'm not showing you any intermediates because I'm confident you can get this. Draw me the mechanism for that NAD+ mediated oxidation of oxaloacetate to malate. Sorry, I said that backwards. Scratch that, let me try again. Draw me the mechanism of NAD+ mediated oxidation of malate to oxaloacetate. Oxidate, that's not a word. I'm not feeling that generous. Oxidation. There we go. The verb is oxidize. Anybody stuck? Need help? So you want an NAD+. Oh. And remember, it's a hydride receptor as Okay, anybody else need help? No, this is gonna be most like, all right. So, as I've talked to a few of you, it's been clear that without any details, sometimes it's tough to know where to start. Once you see this reaction enough, you'll put it together. You saw it last time with the isocitrate dehydrogenase step. We're going to begin with a base removing a proton from the oxygen. See, because this carbon this sp3 carbon in the starting material is going to become this carbonyl carbon in the product. This oxygen in the starting material is going to become this carbonyl oxygen in the product. But notice that the hydride, the hydrogen and its electrons on that sp3 hybridized carbon are not in the product. Where did they go? Well, they went to NAD+. So a base is going to remove this proton from the alcohol. Electrons are going to kick down then to form the pi bond. Hydride's got to leave, and it's got to go somewhere. H- is a terrible leaving group. So it can't really leave on its own. It needs to be received directly by NAD+. And remember that I told you that NAD+ is electrophilic at the carbon that's opposite the nitrogen. So hydride, and you can demonstrate that with the resonance structure that I've shown you before. Hydride attacks that carbon. If we stop there, and sometimes actually I like to draw in the hydrogen that's already there so that you don't mess up and get things wrong, but the hydride gets delivered to the blue carbon. If I stop there, I'd have too many bonds to carbon, so I have to shift these over to form a pi bond, and then these over to be a lone pair on the nitrogen. That gives me oxaloacetate, and it also gives me NADH. And the structure is here, and one of those two, doesn't matter which, it's actually known in some cases which it is, we'll just say it's this one. That's the proton that gets added, that's the H- that gets delivered to NAD+, that hydrogen plus its electrons. Okay, yes?
I don't know if this is a stupid question or not, but can you not do it the other way where the enzyme deprotonates H that's not connected to the alcohol, and then that forms the bonds its own and kicks off?
That's a really, really excellent question, actually, because you're right. Couldn't an enzyme remove this proton? Then these electrons kick down, and then H- gets delivered from the alcohol. I don't know what experimental evidence would demonstrate that. Actually, what you would do is you would prepare a radio-labeled molecule with maybe deuterium here instead of hydrogen, and then you would monitor where deuterium ends up. If it were there and it ended up on NADH, then you would know that it's that hydrogen that got transferred. It makes a little bit more sense to do that because alcohol protons have a lower pKa than protons that are alpha to carbonyls. So it probably makes more sense this way. It's certainly reasonable to do it the other way, and I promise not to give you that option that you just described as an incorrect option and try to lure you into that. Yeah. Okay. You want me to write it down? If I do it, you get an extra credit point. So will you take a loan, a potential loan okay, there you go. All right, other questions about that? So that completes the cycle. Last time, I think you asked the question, where does oxaloacetate come from? And this is where. It comes from the end, and it just goes around and around and around. Okay? So that's a good stopping point for a break. Let's take 5 minutes or so, and then we'll start back up.